Welcome to this brief presentation on our work titled Skill Machines, Temporal Logic Scale Composition in Reinforcement Learning. One of the main promises of reinforcement learning is to one day have generally capable robots that can solve many complex tasks in their environment. However, designing such multipurpose agents remains a major challenge in the field. This challenge is in part due to the difficulty of defining tasks. How can we specify tasks in a manner that is both interpretable and verifiable? How can agents then solve such tasks efficiently with guarantees on their behaviors? This is particularly challenging given the poor sample efficiency of reinforcement learning. Hence, we want tasks specified in a human understandable manner. We want agents that are able to provably solve such tasks without having to do costly learning every single time a new task is presented. One common and natural approach is to specify tasks through formal languages, such as linear temporal logics. Here, tasks are specified using temporal and logic operators over high-level events in the environment. Consider, for example, the safety gym domain where a point mass robot has sensors to detect when it has reached a green button, the red cylinder, or a blue region. The agent may then be required to, let's say, navigate to a button and then to a cylinder while never entering blue regions. This can be specified using linear temporal logic using the shown expression. Such LTL expressions can then be translated to reward machines, which are finite state machines that encode the reward function of the task to be solved. This solves the task specification challenge. However, how can we then solve this task provably without further learning? A common approach in the literature is to do temporal composition, where skills are learned in a way that can then be chained to solve subsequent tasks. Consider, for example, an agent that has learned how to navigate to buttons, blue regions, and the cylinder in the safety gym environment. The agent is then required to solve the following LTL specified task. To achieve this, it needs to eventually reach a button that is not in a blue region, then reach a cylinder that is not in a blue region, and do all of this while never entering a blue region. However, the agent is unable to solve this task by simply chaining its learned skills for reaching buttons and reaching the cylinder, since it has not learned how to do them while avoiding blue regions. It hence needs to relearn new skills for reaching buttons and the cylinder while avoiding blue regions. In general, we can see that during arbitrary temporal logic tasks, there is a super-exponential number of possible Boolean expressions the agent may be required to eventually satisfy. Similarly, there is a super-exponential number of possible Boolean expressions that the agent may be required to always satisfy. We identify these as the spatial and temporal curses of dimensionality present in temporal logic tasks and that remain unaddressed in prior works. We address these curses of dimensionality by introducing the notion of primitives. For the spatial curse, we define task primitives as composable MDPs for eventually satisfying each proposition in the environment. We then define skill primitives as their corresponding world value functions. Similarly to prior works, these can then be used to solve the respective task primitives. But unlike prior works, these can also then be composed to achieve any Boolean expression over task primitives without further learning. For the temporal curse, we introduce the concept of constraints, which we use to augment the state space of task primitives. In the given environment, a constraint is a proposition that an agent may be required to always keep true or always keep false in a temporal logic task. Consider, for example, the task primitive for reaching a cylinder. We show the goals achieved by an agent when the constraint is violated and when it is not. Notice that both goals are still desirable for a task of reaching the cylinder. We now introduce skill machines, which are finite state machines that encode the solution to temporal logic tasks as the composition of skill primitives. The skill machine for a given task can be obtained by planning over the corresponding reward machine. This planning can be done using an off-the-shelf algorithm like value iteration, for example. This gives us the value of each transition with respect to solving the task. We can then select the Boolean expressions to achieve greedily, which gives us the skill composition to follow at each node of the skill machine. By then following this skill machine, acting greedily with respect to the composed value function at each node, the agent is able to successfully solve the task. Importantly, for any new task given, we guarantee that the agent can immediately complete it while adhering to any constraints. For example, without further learning, the agent can also navigate to a hazard, then to a cylinder, and finally to a cylinder again while avoiding hazards. We can now solve any given task near optimally under some reachability assumptions. Interestingly, we show in our paper that the zero-shot policies can also be leveraged to learn task-specific optimal policies few-shot, even when the reachability assumptions do not hold. Thanks for listening, and I look forward to seeing you at our poster 17719 for more details and discussions.